Hey everybody, welcome back. Hopefully a week without lectures felt good. Sorry. Today is going to be one of those days where my phone's going to buzz because sometimes you just can't close Teams. Anyway, right. We got a lecture to give. We're in week 8. So that's crap. Got another dang quiz on the way, and rolling through the end of machine learning. Great. Okay, all is well. Here's where we left off. I had this model working on these tiny images, but even tiny images have a lot of pixels in them. These are small and also grayscale. We're taking each one, or each pixel, I guess, as an input feature, right? Like we know the fact that this upper left pixel is this particular shade of gray. That's a feature. We have a bunch of them. So the sort of scenario I was setting up here was I'm using a support vector machine, not because it's awesome, but because it's expensive, and it will make my point. So that model, that data, 12,000 or so features, took about 8 seconds to train. 8 seconds isn't the end of the world, but, like this stuff is the things are going to grow, the demands of the model are going to grow, your patience is going to shrink. I think we wouldn't, in general, we might be a little worried about that. And I know something about the support vector machine, which is the training is, I think, linear in the number of features. Okay, so now 12,000 features sounds like it might be a lot. If I have half as many, it would take half as long to train, I think. But maybe I don't care about all the features, right? Like just because I have, what if if I'm thinking about it in this world is a CSV file with 12,000 columns, maybe I don't care about them all, right? Like that top left pixel, is there anything Donald Rumsfeld-y about that one pixel? And then these aren't really all truly independent facts about the world. You look at one of these pictures and, well, it's not like it's random noise, right? There's a lot of gradients. There's a lot of very highly correlated things. Mouths are in mouth positions, all of those things. Let's work on that. So one thing we could do, well, I mean, we could have a quarter as many pixels by just having all the images in X and Y, and then it takes about a quarter of the time. Well, yeah, if running time is linear in the number of features and I have a quarter of the number of features, it should take a quarter of the time. And yeah, with a very similar accuracy, because even though these images are small, if they were half the size, you can still tell, okay, that's Donald Rumsfeld, that's George W. Bush, that kind of thing. So, okay, I understood my data, I did something, but let's not choose that solution because I want to choose this solution. Here's the game. I want to decrease the number of dimensions in my data set one way or another, and I don't want to throw away information. I'm going to have to throw away some, right? The whole thing is, right, if I have fewer numbers to describe the world, I can give a less precise description of the world, but I want to do as good as possible, I guess. So this is principal component analysis. And I guess you think about it in a case like this, right? Like this is two-dimensional data, no question. It's got an x-axis and a y-axis that is, two columns in the data set, column 0, column 1. But is it two-dimensional really? If you just tilt your head 30 degrees to the left, it looks a lot like one-dimensional data along that line, and then just a little bit of extra noise perpendicular to that. Most of what's going on, it's one-dimensional, kind of, in a way, if you think about it that way. So the thing that principal component analysis is going to do is, of all the ways you could sort of point a vector in this, okay, 2 dimensions on my slide, 12,000 dimensions in my images example, in what direction can I point a vector that has the highest variance? There's a lot going on in that direction. Call that principal component. And then sort of take the data set and like compress it along that axis. So say, okay, well, we go, 2.6 units in that direction, and then collapse the data along that direction and recurse until you're bored. Obviously, there's a lot of math in there. And I guess the thing I'm imagining here, like I draw the two-dimensional data and I think about the images and I think, okay, there's a lot of correlation between some of the pixels. I don't know, along the forehead part of the image, those are very highly correlated. They're not all exactly the same, but they're very correlated. So there's two dimensions somewhere in there that look like this, and of course, hundreds of other ones. Find the ones where the most change is happening in the data set, call those principal components, and that's sort of the most information you can get with one number is that first principal component. And then recurse, and then recurse either until you're up to the same number of dimensions you started with, in which case you're losing no information, or until you stop, in which case you're losing as little information as possible. So there's a thing for that. I've decided on 2 dimensions here. I started with 2 dimensions, so I shouldn't be losing any data. But what we found was the first principal component was that one, which visually is the red arrow on this plot. And yeah, that's the direction in which most of the variance in this data set is happening. And then once that's gone, like once you sort of smash things down along that axis, well, there's only one dimension left. It's perpendicular to that, and it's the purple arrow. Okay, cool. And 99% of the changes in the data set can be explained by that first principal component. That's great. That's a lot of information for the first number and relatively little information for the second number. Great. If you do that transform, so basically take the data, run it through that transformation, and then plot with the new X and new Y axis, you get that. And yeah, right? If I get to tell you one thing about this data set, or a point in this data set, where is it on the red line? That's the most critical thing. Where is it on the purple line? It would be nice to know that too, but not my first concern, I guess. So we can do that. I can undo it as well. So I can do that transform or transform back to my original basis vectors, I suppose. And I should lose nothing. And that's, as within floating point rounding error of nothing. The other thing that you can, I guess, the other reason you might think I have too many dimensions here is I want to make a plot and my screen only has 2 dimensions on it. So if I have 30, I believe, dimensional data, well, it's hard to plot that. And I was struggling with that actually in, whichever notebook that was. Where I had 4-dimensional data and it was kind of weird and artificial. So this game might not have worked, but in any kind of real data, I can do this. And I can say, well, I've got 2 dimensions on my screen, take this data, smash it down into 2 dimensions, losing as little information as possible, and then plot it because now it fits on my screen and I get this. This doesn't tell me everything about the data. There's 28 dimensions that I'm not showing you, but these are the 2 most important. And yeah, all of a sudden it seems obvious why this classification problem worked. There is some separation. If you look at sort of the right things the right way, there's almost a linear separation after the transform. And if I kept more than 2 dimensions, I probably could make an even better distinction between these data points. But I think this does help me understand the data. And boy, I wish I knew, like, it could be, again, red data is not cancer, purple data is cancer, maybe. I'm seeing a lot more variation in those data points. Maybe that's interesting. But I just have something I can look at now and try to figure out this data. This is another handy trick. And remember, you're losing information here, right? Going from 30-dimensional down to 2-dimensional, definitely information is getting lost, no question. It's just as little as possible. So in general, we're doing dimensionality reduction here. Maybe it's for a plot. I think that might actually be the most useful one, in the next few months of your life in this course. But what I've done here is, again, where the support vector machine was a little expensive computationally, done the principal component analysis, dropped it down to 250 dimensional data, and then got a not so different score a lot faster. So yeah, like I started here and I said, oh, I am mad that this takes 8 seconds. 83%. Okay. If I reduce to 250 dimensions, I could have chosen a different number. I could have chosen 500. That might have gotten me a little bit better score and a little bit slower time. I can understand that images are images and can be scaled this way and get a very, very similar result. It depends what you're doing. And again, I've had to choose something here where number of dimensions matters. Basically, and I see this happen where people on their project, and I've warned about this before, think, I'm going to use as many things from the course as possible, and that will be a good project. Well, look, if you use principal component analysis, you are throwing away information. And if you use it for no reason, that's dumb. You should lose marks for that. And I will tell you, don't do that. That's dumb. But if you need to, if you have a reason for it, great. Just out of curiosity, I tried this, and this took the first image from the validation data I had that day, the Colin Powell image of whatever, he doesn't look happy in it. But this is do the principal component, transform, and then inverse transform. And yeah, like a little information is lost, obviously, right? Like it's not exactly the same image before and after, but it's pretty close. And I guess, if you look at it the right way, you can still tell who it is. And well, yes, right. You can almost as well as before tell who that is, or this machine learning tool can tell who it is. After the principal component analysis, cool. So yeah, there's this overlying if in this principal component analysis. If the number of dimensions is a problem, one of the reasons it's a problem is like computation time or memory or whatever. Maybe it's my screen only has 2 dimensions, so I have to plot with 2 dimensions. So again, I think it's a technique worth at least remembering exists. It is what it is. Don't use it randomly. Use it when you need to. I think that's true of everything. Okay. Here's a much more real problem that can occur, may occur, to some of you will occur in the project on your data sets. And the problem is something like this, where you have categories that are not equally represented in the data. Sometimes that's just because they're not common. Whatever's going on here, maybe class B is just not a common thing. But remember what we're doing when we're creating a classifier with a machine learning tool. What can the thing produce to get a good score? Well, return A on this training data would get a score of 0.99. That's pretty good. That's a useless model, right? Like going through this whole thing and saying, I'm doing machine learning, look at me, I'm a machine learning expert. Look, my model has a score of 0.99 and my model is actually just return A in all cases. Well, you're not so much of a machine learning expert, are you? And I say this because I almost did it to you, past versions of you. I found this data set, this seismic bumps data set that's something about, I think seismic bump means something like mini earthquake in this context, in a coal mine. And, if I was working in a coal mine and there was anything that could be described as a bump, I would like to know when that was about to happen. That would be super. So I tried this. I took this data set, I ran it through something, and I got a score, and I thought, oh, good, the score is good. Okay, exercise problem. And very nearly some past class almost got this problem. But of course, what I realized was most of the time this doesn't happen. Most of the time, there's no little earthquake sort of thing. So it's super, super easy to get a score of 93 point something on this data set, but cool but useless. So I have the full code on this data set. If you want to play around with it, it downloads its own data. The first time you run it, okay. And what happened is, I guess probably their README is the best thing. It's not beautiful numeric data, right? Which is a good, yeah, like that's not always the case. There's columns like this that are, you know, some expert went out in the mine and like poked around and hit some rocks with a hammer or whatever they do, and they said A, B, C, or D. That's not a number. If I try to throw that into any of the machine learning tools, it will throw an exception. Fine. I should deal with that. There's these shift column that's basically like, what are the coal miners doing today? Are they, I don't know what you would do to prepare to get coal. Drill holes where the dynamite goes, maybe, versus actually dynamiting and digging, whatever. Okay, maybe that matters, right? Like maybe the dynamiting is part of what causes one of these seismic bumps, whichever side of that. So okay, maybe I need that, but it's not numeric. It's either a W or an N. And then there's a bunch of other stuff that is numeric, and maybe some of it matters, maybe some of it doesn't. But we do hope that the machine learning tool will sort out, okay, this is important, this isn't. So these columns, and there's a few of them that are these ABCD scores produced by an expert. I am going to, well, they're definitely ordinal, right? No hazard, low hazard, high danger, which is a lot of high. So those are definitely 4 ordinal values. I am going to choose to make them numeric this way. Just A is a 0 and B is a 1, C is a 2. Maybe I should talk to the seismic assessor or whoever in this story and say, hey, you know, how much worse is a B than a C? Is it twice as bad? Is it 10 times as bad? And give better numeric scores that way. But that person doesn't want to talk to me, I would guess, and I'm just going to say 0 to 3. So that the other thing I have, again, these categorical columns, right? So this one was ordinal. I decided to make it numeric in a reasonably obvious way, I think. This categorical one, it's not obvious how to turn categorical data into numeric data. The thing you do typically is one-hot encoding. So it's basically for each possible value. So from this one column, for each possible value, create a new column. So in one column is going to turn into 2 columns here. If there were 10 categories, it would turn into 10 columns. And each one of those columns is a binary, like a Boolean, basically. Am I in that category or not? So if I did have 10 categories here, each row would now have 9 zeros and a 1 in, you know, whichever spot corresponds to being in that category. Now I have something numeric that is something that well, obviously I can do calculation on it, which I need to do for all these tools. And I can represent this categorical fact with which one am I in. So like, don't fall into the, you know, if these were 4 categories that were not in any way ordinal, turning them into 0 to 3 is a total lie, right? I am passing this number into the machine learning tool and saying like, oh, this one is twice as much as that one. So I made the call that I can do a like twice as much kind of interpretation of these ABCD values. But N and W, those are just straight categorical. I better do something more clever. So I'm going to do a function transformer for the ABCD columns. And, you know, I bumped around in pandas for a little bit. And then I found this thing that is, take this thing, run it through this dictionary. So look up, they come in from this data set as byte strings. So the byte string A corresponds to 0, B to 1, C to 2, D to 3. and just map the 3 columns that have that property into their numeric version, great. So I can function transform that. The one-hot encoding, I don't want to do it to all the columns. I just want to do it to this one column where it matters. And once again, it took me a while. Like I poked around in scikit-learn, tried to figure out how to do this, eventually found, oh, there's a thing for that. I'm sure I Googled scikit-learn transform only some columns, and I found this. So those 3 columns go through this transformer. This one column goes through that transformer. That's part of my pipeline. I think there's a few missing values in there. Well, I'll do a mean imputation on them just so something's in there. And I used a gradient boosted tree classifier, played with some parameters a little bit, got some decent enough results, and I got here, right? And I think, oh, and this is where I was in the assignment question, right? It's like, hey, cool, 92, that's an assignment question, great, send it, right? And then luckily I looked a little closer. So the classification report that we've seen once or twice, okay, tells this story, right? Where category 1 is never predicted. All the things that are really in category 1 get put into category 0. Okay, right, wait. I've just done all that work just to create a model that is return 0. That's annoying. Or, so yeah, we've seen the classification report, the confusion matrix, same story, right? Like I want to see a perfect diagonal line here. What I see is, oh, everything just ends up over there when we predict. Either one of those will tip you off that this is what's going on. So what do I do? And I guess maybe I should use the term, right? This is imbalanced training data, where some of the categories are not very well represented in the training data. In this case, at least, because they're just rare. Most days, this thing doesn't happen at the coal mine. Great. I would not want it to be an equal probability situation if this dangerous thing happens to me. There's a few ways to deal with this. I will let those blog posts stand on their own, I think. You can sort of adjust the model and decide to look for these. Maybe you can generate more data, right? Like maybe you're in a situation where send the experts back out into the coal mine or whatever. I don't have that option because I'm using a data set I found online. So I'm going to choose this one. I'm going to rebalance this data set, which is basically to say, well, I have my rare category. So I'm going to take all of the data points from the rare category, hold on to those are precious. From the other category, I'm just going to randomly sample an equal number. So whatever this was, if there are 15 of them or whatever the number was, randomly sample the same number from the other category. Then, well, once I put them together at least, I have 2 categories that are equally represented. I've had to throw away a bunch of data to get there, but maybe it's the best I can do. So now, train, test, split, train the model, etc. My score goes down. Like this is a much worse score than I had before, but at least now my model is doing something. I would not want to go into a coal mine on the basis of these predictions, or frankly ever, but at least this model is now doing something, right? Like there's some value to this model, and then we can start arguing about like, oh, maybe we can do this or that to increase the score. Again, maybe more data would do it, maybe a different model would do it. Maybe there's something we don't know. You talk to the coal mining experts. Where is it there? Like there's all these categories of different sizes of seismic bump. There's the hazardous seismic. There's the number of bumps recorded in the previous shift. All of these might be really useful, and maybe there's something else. Maybe it's the number of bumps recorded 3 shifts ago that matters, or whatever. And maybe if I was an expert in coal mines, I would have a sense of that. But this is something to keep an eye out for. It's something that can happen. Of course, very often the task is to detect things that don't happen very much, right? Things like the credit card fraud example. Well, almost all credit card transactions are not fraudulent. So you can get a very good accuracy score by just saying no. And if anybody pays you for that, well, more money than brains. And the other reason I wanted to sort of go through this example is this, again, just dealing with this non-numeric data, because whatever machine learning tool is going to throw an exception if I don't make those changes, right? If I just didn't do this, yep, got to be afloat. Okay, and then I assume I inserted that imputer for a reason. No, maybe. I don't know. I assume there was missing data in there. Maybe I just did that as part of the example. But yeah, so I get a score. It's worse, right? It's very easy to look at a score and think that number is big. I am happy, but well, maybe not. Okay. Let's fill in one more classification technique. And well, again, we have the I'm going to think about probability distributions. I'm going to think about similarity to existing data points. Fine. Oh, I didn't include trees and forests. Oh, no, sorry, I did there. I'm going to think about a nested if block kind of thing. Okay, cool. Let's I guess think of one more I don't know, basic way to think about classification that will make sense. Okay, I'm going to take my data, and I'm just going to think at least about kind of one row at a time, just because this is the way the notation usually works for neural networks. And then, of course, the thing I want is like, well, which category am I in? And what I'm going to think of here is like, well, I have these categories, these M features that I know about the world. Maybe there's something about being like having a large feature number 2 number that makes me think, oh, I'm probably in category 7 here. Or if I have a really low, like a negative number, that means I'm in category 12 or something. That's what I mean by sort of how much each feature matters, right? Like each feature is sort of an either positive or negative predictor of being in a certain category. Maybe if I can come up with some weights like that, it's like, this is how important this feature is to being in this category. Again, it might be a negative thing. And then I'll just take those like scores of how category I-ish I look, choose the biggest one. Maybe that could work. So I take this data that we've seen before, same thing that's been in a bunch of slides here. But now I'm going to do this calculation. For no good reason, I'm going to calculate this number. And that's my score for being in the blue category. If that number is big, that is evidence, in air quotes, that I'm in category blue. And I'm going to come up with 2 more calculations like that. A calculation for being in category 1, calculation for being in category 2. Whichever one has the largest categoryness score, I'll choose it. Obviously, these aren't truly magic numbers, but those are the ones that I'm using on the slide. And what I get is this. So once again, the background is the category that's selected. I want my training points to be on the matching background color, and they mostly are. So obviously there's something about this calculation that I just made up that kind of works. There's something about this 17.2 plus 1.9x1 and 3.2x2 that is somehow useful for saying, oh yeah, you might be in category 1 there. And this is how those boundaries work out. Okay, hooray. And we're going to go one step farther. I'm going to turn this into a probability. So those calculations from back here, I'm not just going to do the calculations. I'm going to do those calculations, and then I'm going to run them all through the softmax function, which is this. I don't think the details of the calculation matter much to me, But I do know that, okay, I have this number, e to the whatever, over the sum of all of the e to the whatevers. Well, e to the something is always positive. The sum of, so thing divided by sum, so all of these together are going to sum to 1. So if I have a bunch of positive numbers that all add up to 1, that at least like structurally looks like a probability. Is it fair to call it a probability? Maybe not, but I'm going to treat it like one. I guess the other thing is the softmax function is monotonic. So again, big number for this calculation will still be the biggest number. I'm just going to scale things so they sit in a reasonable range, and I now think of them as probabilities. And, you get something like this, where like for the second data point, okay, I'm very much not in category blue for whatever's going on there. It's kind of a close decision whether I'm in category 1 or 2. So what is that? 0, -3. 0, -3. Yeah, so it's up there. It's far away from being blue. It's pretty close between red and green. That's why I chose that point. And you can kind of read that out of these probabilities. Okay, cool. The thing I just invented is a perceptron. Invented is an aggressive description of that. But anyway, so I've got my column of 1s there, so I can have this like intercept part of my calculation. I'm going to multiply that by a matrix that is a matrix of all of those numbers that I made up a couple of slides ago. I'm going to call those weights. So it's, again, how many times category 0, how many times, feature 0, how many times feature 1, how many times the bias. Put those together. That's my weight matrix, or my weights. And then I'm going to run it through an activation function. The one I choose for this moment is softmax. Or I guess if I like linear algebra, I could express it this way. Take my matrix of observations, multiply it by my matrix of weights. That will give me, for each thing, for each like row, a score for each category. And then run it through the activation function. Then I can choose the largest thing on each row. That's the winner. Well, okay, that's cool. Like, it's cool that this is a matrix multiplication. Because like computers are good at matrix multiplications, so are graphics cards. Or like you might visualize it like this somehow, which is, okay, each one of these lines has a weight on it. 1 times this weight plus x1 times that weight plus x2 times that weight. Add those things together, run them through the activation function softmax, and then call that the probability of being in that category. Again, choose the largest. Obviously this story about magic calculations is not really magic. It's what the multi-layer perceptron does. And again, this calculation I've described is choose this linear combination, choose the largest is a perceptron. I don't think I have the link there. I feel like I've always felt like perceptron is a like unnecessarily a sci-fi sounding name for this. Like it's some linear algebra. Like let's just relax. The reason is that we started here. Like the perceptron was invented earlier than you would expect, when the programming computer was like, make all these wires go. Boy, I guess you don't get a high-res photo from back then either. Yeah, like in 1958, okay, like if you're going to do this in 1958, you get to choose a real sci-fi name for it. Like that seems totally reasonable to me, and the name has stuck. So I'm going to use the multi-layer perceptron classifier. I do not yet have multiple layers, which is why I have an empty collection of hidden layer sizes. We'll get there. I can train that on the training data, and then I get these numbers, which are the numbers from a few slides ago, right? Like that's the calculation that's being done. This many times the bias, this many times each feature. That's the score for being in that category. Because I have a classifier here, there's implicitly the softmax function as the activation on that last layer. I get probabilities, which is what I'm showing you here. And score on the validation data, I get a pretty good score. So this is like neural networks version 0, 0.1. And it's not bad. Again, like if it was 1958 and I could do this much machine learning, I would be very happy. But let's move on. So the neural network is basically that, but more. So we're going to take the inputs, we're going to run them, like multiply them by some weights, add everything up. I have this activation function to kind of get the numbers into a range that isn't too crazy. I guess softmax is getting the numbers into a range that lets me think of them at least as a probability. Getting the weights out of the training data, that sounds hard. Well, there is a thing for that, unsurprisingly, because you just saw it happen a few slides ago. What I want is that, but more. I want more flexibility. I want to be able to make more advanced decisions based on more advanced calculations and bigger data sets. That's a neural network. It's basically extra layers of that exact thing happening. Call it a neural network. So maybe this. So my inputs are fixed, right? If I have two-dimensional input data, or two features in my input data, I'm going to have two things here because I've got to get those numbers to go somewhere. I've got three categories, red, green, and blue, or whatever. So I have to have three things in my output because I have to have a probability for each category. But in between here, I can kind of do whatever. I have chosen, at least in my example, to have two layers with 4 nodes and 3 nodes. I think I played around a little bit and this seemed to work well. I do, right. I do have the activation function. So there is, like, coming into this node, I add up all of the inputs and I go through the softmax activation function. For these other nodes in the middle, I can choose any activation function I want. I'm not going to choose softmax. That's the wrong thing for that job. But okay, we have this. I don't know what's going on in those middle layers. They just are. They are useful, halfway points in my calculation, and that's all, basically. For the activation function in the middle layers, basically what I want is I want to not get numeric overflow, right? Like if I'm doing a whole bunch of this stuff, maybe these weights are really big. Like maybe, the weight on this edge is like 10,000. Okay, sure. Take this number, multiply it by 10,000, put it here, and then add a bunch of other stuff to it. Well, if I have a whole bunch of like big numbers and big weights, I'm going to end up getting numeric overflow, and this is annoying. And like if I just have a big number, that's going to totally take over the calculation. I don't want all that to happen. So something like the sigmoid function, logistic function, I guess the logistic function that is a sigmoid function, but anyway, is this, right? So it's big numbers go towards 1, small numbers go towards 0. Great. It will keep everything from exploding in my calculations here. Or like hyperbolic tangent, which is the dotted blue line here. This is like big numbers go towards 1, small numbers go towards -1. Same exact kind of thing, with some different details. Basically, it's don't let my numbers get too big or too small. Keep them within reason. That's what my activation function is going to do before the last layer. In the last layer, I'm going to choose softmax so I can pretend these are probabilities and also get them into a decent range. So the number of input layers, or the number of nodes in my input is fixed. The number of nodes on my output is fixed by the number of categories. In between, I have a choice, and I'm going to make my choice. And also in the middle, I have a choice of what activation function I want to use. I choose logistic. Then I can train in the training data, score the validation data, and I can get a nice score out of that. If I have a look at what's going on in the data, those seem pretty reasonable. Like those seem like reasonable decision boundaries on this data. Sure. Again, I like that. I think I trust that. I guess I didn't print out the training score versus validation score, but it's good. Like I don't think I'm overfitting data on this based on that at least, or based on this visualization. I'm pretty happy with those boundaries. I don't think that's too crazy. The problem is this gets out of hand pretty quick. I have 39 weights. Where are we at here? And that's basically each one of the lines I've drawn in this diagram has a weight on it. So it's 39 of them. When I'm training on the training data, I need to like sort out 39 parameters. That's a lot. The way it's done, well, I guess it's not a lot if there was a formula for it, but there's not. What you have to do is fill in some initial weights. Maybe those are random numbers, maybe they're all 0 or who knows. And then go through an algorithm that's like, okay, take some training data, put it through this neural network and decide, am I happy or sad about the output? And if I'm sad about the output, which way would I like it to move? And then propagate that back through the entire network, sort of pushing the weights up or down in order to make them a little bit closer, and repeat. This is a massively computationally expensive thing to do. It is why Jeff Hinton from University of Toronto won the Turing Award and basically every award that's possible to give to him, and he deserves it. But it's expensive. And okay, expensive in computation is one thing. It's also expensive in training data. If you have 39 weights to fill in, well, I bet if I have only, a few hundred training points, that's kind of just not enough to sort out what all of those things should be. And I think the evidence of that is every time I run this, I get a different picture. I get different weights and I get a different visualization of the boundaries here. And I think that's because I'm just effectively undertraining a network of that size. But that's a pretty toy-sized neural network. Now, it's a toy-sized data set, but this just happens. Neural networks are really hungry for training data, which means, well, if I have a limited amount of data, I might be in trouble. I'm now limited in how big my neural network can be. I can make a much, much bigger neural network. I could have hundreds of hidden layers and each one could have hundreds of points in it. And I could hook things up in a bunch of different ways too. And if I have a few thousand training points, that's a good story to tell, but completely pointless because I just can't train it with the data I have. So this seems to be the effective limitation on neural networks. It's, if only I had more data, I could create a more complex model and then I could train it and then it would succeed. But as it is, no. So the other thing as neural networks get bigger is the computational expense. And this is why training neural networks and GPUs start to be spoken of in the same moment because, well, a GPU is basically a big linear algebra chip. And well, that backpropagation algorithm is a whole bunch of linear algebra. Okay, cool. Scikit-learn doesn't do that. Scikit-learn does it on the CPU and everything is fine if your data is small and your neural network is small because that's their problem domain, right? They're not trying to do something else. There's a bunch of other things for that. I don't want to dwell on them. And things that are sort of a little bit more competitors of scikit-learn, that do machine learning things, and then things that are a little bit more competitors of NumPy that let you do matrix-ish things, but on the GPU. And whatever GPU works, I don't know. So just because what the heck, I wanted an example of it. I decided, okay, I'm going to do this in Keras, not because it's better, but because I found a tutorial that let me get these slides together in a reasonable amount of time. And what I found out was, okay, scikit-learn will take a neural network with this output and choose the highest one and say, oh, you have chosen category 2 here. Keras would not. I have to sort of do that transformation myself and say, okay, for each data point, my output is not 2. My output I would like is this. I would like you to say 0 probability of being in these 2 categories and 100% probability of being in that category. This is what I want to come out. I used a scikit-learn thing for that just because it's the one I found first. And then, well, again, I have to spell it differently, but this is the same neural network as the scikit-learn example. I have 2 input features that are connected to 4 nodes in the first hidden layer that are connected to 3 nodes in the next hidden layer that are connected to 3 output nodes, and I need that because I have 3 categories. I'm going to choose my activation function the same as I did in scikit-learn. You know, I have more to say because there's more options, there's more flexibility. I have to like the way I call model.fit is different, but the basic thing is not so different. I call .evaluate instead of .score. Fine. This would, I think when I did this slide, it just ran on my CPU because I couldn't be bothered to set up CUDA and everything for it. But if I had a bigger example and I was going to do it that way, I could have all of this done in my GPU and that would be faster, ? It should be anyway. So like I said, I think very often neural networks are the wrong thing. And like, who was I talking to? Well, I shouldn't out anybody. I was talking to a colleague who said, yeah, my grad students keep coming in and saying, oh, I think I'm doing something wrong. The neural network gets a worse score than the, you know, Gaussian naive Bayes or whatever, or the random forest. And my colleague has to say, yeah, because we don't have enough data to train a decent neural network here. We have enough to do a random forest. Or this problem is not hard enough to need some massive neural network. It's hard enough to need a nice little random forest, and that's really fast, and we should just do it that way because it actually works for our data. Yep, deep learning and neural networks are really cool, and like 10,000 is not the number, right? This is part of the reason that like the massive machine learning is in the hands of massive companies, because you need a lot of data and then you need a lot of compute power to train on that data. I guess we thank the investors for dumping their money down this black hole to our benefit, ? Anyway, I will point out here, like data augmentation, this is one of these things that should make you feel like maybe you're doing something wrong and this is a little dirty. But if what you're doing is an image recognition task, I think is the scenario here, and I want to take this image, I want the output to be cat, and some other image, and I want the output to be dog. Well, okay, if this is a cat, or if I take and I rotate the image, or I zoom in or out by a few %, it's still a cat. But now one row, one training point has become 7 training points. Well, okay, I'm still recognizing the same cat, right? I still might learn that cats are this particular, color and have eyes that are particularly that shape or whatever, because all of these training points have that. But at least I'm not recognizing a cat that is in specifically this orientation. If they're turned a little bit, I would still recognize cat. This is the idea here. It might be possible. I think it's something you should undertake with caution. Okay. That is a good spot for a break, if not a little bit over. I'll see you in the next video.